So we talked about carts in CSPs. So here we'll be using similar kind of ideas. So we'll be defining a cart that will separate out the decision variables from the contradiction, right? So basically why we are doing this? So that is to see which decision variables lead to this contradiction, right? So for example, we can define a cart here. So what our decision variables are? Decision variables are this, right? And what is our contradiction? Our contradiction is this. So we are trying to cart these nodes from the contradiction node. So that means we have a cart here, which is our cart 1, right? So what cart 1 will give us? The cart 1 will give us the assignments. So we'll be picking up those nodes which have at least one outgoing edge that crosses the cart, right? So you see this A equal to true, it is having 3 outgoing edges that is crossing the cart 1. So that means we'll be including A equal to true in our cart set 1. Of course, we should also include, should we include B in our cart set? Any idea? So how we are including this? We are including the node that is crossing the cart by at least one outgoing edge. So I do not have any outgoing edge from B. So that means there will be no crossing of an outgoing edge from B to the cart 1. So that means I should not include B here. With the similar logic, I will not be including C here, but I will be including X equal to true. So this is my cart 1. So there might be another cart, right? So I can have another cart that will separate the nodes from the contradiction, right? So our cart 2 will contain what? It will be containing A equal to true because A is crossing this particular cart. So A equal to true will be here, and we'll be having so this Y equal to true. This particular edge is crossing the cart. So we should have Y equal to true, right? Now you have another cart which is in the form of, say, this. And this will give us our cart 3. And what cart 3 will contain? Of course, A equal to true, and then Y equal to true, and Z equal to true, right? So basically, these are the kind of 3 conflict-driven clauses. So these are the 3 CDCs. Right. Now, from the CDCs, what we want to finally get, we need to get the empowering clause. So we need to find out the ways to get from CDC to the learned clauses. So basically, these are the clauses that will lead to contradiction, and the learned clauses is the set of clauses that can be added to the knowledge base without any contradiction, right? So these learned clauses are implied by delta, right? But not there explicitly, right? So let us take one example conflict clause. Maybe we know that A equal to true. This is one. I think this is cart set 1. So let us take cart 1. A equal to true and X equal to true. What does that give us? That gives us, that leads us to contradiction. Any question? Okay. That leads us to contradiction. So that means we are doing this conditioning and we are getting a contradiction, right? Now, if we apply a reverse logic, that if, so how will this look like? This looks like this A equal to true and X equal to true. So this will give us a contradiction. What does that mean? If we take a negation of this should be implied by delta. Do you agree on this? So I say that this is the kind of clause that leads to contradiction for this delta. So that means the negated clause of this is implied by delta. I think that is agreeable to you, right? So that gives us the notion of these learned clauses, which is our alpha, and alpha is basically a negation of our CDC. So this is basically a negation of our CDC, right? And if we set this, so what we will be getting, not of A or not of X, which is not of A in the clausal form. So this is in disjunction form, right? And we know that this delta implies alpha. And this is what we mean by learned clauses. Now, by this, if we go by the example that we are doing, we have got three such alphas, alpha 1, alpha 2, and alpha 3. Now the question is which one to choose. So we'll set up a method by which we'll be choosing one out of these three. Again, I'll not be going to give you any proof for that, but all these modern SAT solvers, they make use of these strategies. So this, from the learned clauses, we'll get to empowering clause. So this is our ultimate goal. So for that, we define something called asserting clause. So let me first write down the clauses that we have obtained. So we have got three clauses in cart 1. We have got A equal to true and X equal to true. In cart 2, what we have got, A equal to true, Y equal to true. A equal to true, Y equal to true. And in cart 3, what did we get? A equal to true, Y equal to true, Z equal to true. A true, Y true, and Z true, right? And the level for this is 0, level for this is 3, level for this is 0, level for this is 3, 0, 3, 3, right? Now we define something what we call as asserting clause. So asserting clauses are those clauses that includes only one variable assignment at the last decision level. So let us take for these three, which one is asserting clause. So we are having two assignments, and in the last level, which is 3, we are assigning only one value. So this is one asserting clause. So cart 1 should be one asserting clause. Cart 2 with a similar logic would be an asserting clause. But here in cart 3, you see, we have assigned, made decision on two variables, y and z at the third level, at the last level. So by the logic, by the definition, this cart 3 is not an asserting clause. So these are the two asserting clauses, right? And either of these two can be used as the learn clauses, the empowering clauses. Now, at which level we'll be backtracking? So that is another question, right? For that, we'll be defining what we call as assertion level. So assertion level is the second highest level in the clause. So let us check. So you have got two qualified for this. And for this, what is the second assertion level? Second highest level, the second highest level is 0. And for this, the second highest level is 0. So if we select either cart 1 or cart 2, we have got the assertion level to be 0, right? So what we'll be doing, we'll be backtracking to the assertion level, and in this case, which is 0, right? So basically, it is the deepest level. If you go back to that and add this conflict defend clause, this will allow the unit resolution to derive new implication, right? So we'll be backtracking to this level, and then we'll be adding this asserting empowering clause, and then perform unit resolution, and we'll see that we'll be detecting the contradiction pretty earlier, right? So now we have got all the ingredients to define our algorithm for this modern SAT solver. So it is more advanced version of DPLL. So let us name this to be, say, DPLL plus. Right. So I'll just give you the blueprint. The description of the exact algorithm is there in the uploaded video. I'm not going to discuss that today. So the first step is to identify the empowering clauses. So which is basically your asserting clauses. The second step is you backtrack to the assertion level, right? Now add the empowering clause. At that point. And then you apply unit resolution. So this is what the blueprint of the algorithm, and the complete algorithm is given in the uploaded video lecture. So I'll just end this using doing an example as with the same knowledge base that we did earlier, right? So I guess I don't need to do much here. So basically we start with, okay. So you'll maintain two data structures. One is D. We start with empty, and we have one data structure which is kind of set of learned clauses, right? So again, we start with empty. So we have the first iteration, right? So in the first iteration, we'll keep on adding a equal to true, b equal to true, c equal to true, and x equal to true. So this is the assignment we did, right? Now at this point we have a contradiction. As we have a contradiction, we have one opportunity to find out the empowering clauses, and we have already seen the method to find out the empowering clauses. So we found out one empowering clause like this. And what is the assertion level? We also got the assertion level to be 0, right? So what we'll be doing, we'll be removing all the assignments that we did after this m equal to 0, right? So that means the D will be revised to be a equal to t, and all these things will be wiped out, right? And what would be our gamma? Gamma will contain this newly learned empowering clause, right? And in the second iteration, what we'll be doing now, what we have got delta, and this to be not of a, not of x, right? And what is our d? D equal to a, d is a equal to t, what we have done in the last iteration, right? Now here we can quickly draw the implication graph, right? So basically, we have set a equal to true, right? And if we set a equal to true, which this graph we have also drawn earlier, then we will derive at the same level x to be false. Now these two will give us z equal to, at the same level, true, using the fourth clause, and using the sixth clause we'll be getting a contradiction. Second, we will be performing the cut. So the one cut that we'll be getting is this, right? And what is the kind of set of variables that are involved in this cut? We have this a equal to true, right? So this is our CDC. Now how to convert this into an empowering clause? So our alpha will be the negation of this, right? So now we have our asserting clause alpha to be this, right? Now what is the level of this? The level of this is 0, right? Now we need to find out the second highest, right? Now we do not have any second highest because we are having only one level. So in that case, we have a convention to take this m to be -1 if we have only one clause in the one variable in the CDC, right? Now if you do that, what will be D? D will be empty because we'll be removing all the assignments after m equal to m plus 1, assertion level plus 1. And what our delta will become, gamma will become? Gamma will be not of a, not of x, and not of a. Now, as you have this, we have learned one unit clause, right? And what is the implication? We need to make it to be true. In order to make it to be true, I have to make this to be false. In order to make not of a to be true, I have to make a to be false, right? Now this is what we have. Now in the third iteration, what we will be doing? We have assigned a equals to false. What is the implication? We have something like, say, a implies we have ab, right? The first clause was ab. Now, as soon as we set a to be false, by using clause 1, at the 0th level, we have to assign B to be true, right? So as we set B to be true, I do not have any other unit resolution to perform. I do not have any contradiction. So that means we have arrived at a solution that this is satisfiable given A equals to false and B equals to true. So this is the instantiation of the variables which leads delta to be SAT. So I think this is more or less about the SAT solvers. So what we have done, if we try to summarize, we have tried to define the SAT problem and taken some problems from different domains and tried to encode them into SAT representation. Then we focused on mostly on designing complete SAT solvers. But that does not mean we do not have any incomplete SAT solvers. So there are many methods which are heuristics based, and they will try to solve the problem in a pretty faster manner. But in some cases, they might not be able to find out a satisfiable assignment, though the knowledge base is satisfiable. So that's why they are called incomplete solvers. So I have not talked about really the incomplete solvers. So I think if you are interested, there is a nice book about satisfiability, which we call as Handbook of Satisfiability. Actually, all the materials that I have used here in this particular module has been picked up from the 3rd chapter of this book. So I'll share that chapter with you, maybe in the MST, not if not in the course web page, right? So I'm done with this SAT module. If you have any questions at this point, I'll be happy to answer. Okay, well then. So in the second half, we'll be having a demo on a SAT solver, which is, we have just mentioned, GSHAF, and try to see whether we can experiment with some of the ideas that we have talked about in this class, right? So with this, more or less, we are done with uh, the discussion on the kind of reasoning which considers our world to be entirely deterministic, right? So just give me a second. Just give me a nod. I have just shared a new slide on reasoning with uncertainty. Just let me know whether this is visible or not. Shurashish? Okay. So until now, we have talked about logic and resolution techniques and other things, SAT solvers, CSP. All of them, they have an underlying assumption that our world is deterministic, right? But you know, only certain thing that is there in life, that life is full of uncertainty, right? Whatever you try to do, you make a decision. You make a decision by partially observing the world around you. You do not have a full observation of your world that you see, right? That is one thing. You have uncertainty in measuring different facts about the world. The second thing that is true is that you are not pretty much sure whether your action is also going to be deterministic. So that means the outcome of your action is also not always certain, right? So you can try to do something, try very hard, but the outcome may be positive or negative, depending on many factors. And some of the factors we do not really know. So the point that I'm trying to make is we are living in an uncertain world. And if we want to design an agent that will be interacting with this uncertain world, so this reasoning with this deterministic world is not really sufficient. We need to we need to reason with the world that is uncertain. And that's why this particular module is very important while we try to develop practical systems. Maybe a robot, maybe a software agent that performs some task for you. Whatever you think about, the world is uncertain and this uncertainty has to be modeled. And that's why we should be talking about reasoning that captures the notion of uncertainty about the world and as well as the outcome that can can we have when we perform some action, right? So we'll be spending some time on this. So I'll just discuss the introductory part of this today. Uh, then maybe in the next class, we'll be dealing with the details of the things, right? So as I have mentioned that till now we have the world view, like the world is completely observable, that outcomes are deterministic, and while we define a state, the state has complete information. You know that if I do this, I'm bound to get to a particular state, right? But life is not that easy. First of all, the world is partially observable. The outcomes, they may not be deterministic, and in many cases you do not have the complete state information, right? So if we talk about an agent in an uncertain world, so there are plenty of examples that you can talk about. So for example, a robot has been asked to pick up, say, an ice cream, a cup of ice cream that is kept somewhere in the uh, room. But the robot does not have the vision sensor. It just can smell, right? So the robot does not have the exact location of the object. The robot will do some trial and error, follow the trail, and in following the trail, the robot may be deviated to some other path. Maybe the robot can again backtrack to certain paths. You see, lots of uncertainty is involved in this particular task. Talk about doctors. The doctors, they diagnose the patients based on some observations, right? Now, while we are doing certain observations, one way to observe is to observe the symptoms of the patient, whether the patient is having headache, whether the patient is having fever, and maybe the doctor will ask or advise the patient to come up with certain tests. And again, the outcome of the tests, many of the cases, they are not that deterministic, right? So that means the doctor does not have the complete picture about the state of affair of the patient, right? And in spite of that, the doctor diagnoses something, right? Comes up with certain decisions. And the outcome of the decision again is uncertain. Given that the doctor is following certain treatment, that means the doctor is taking certain decision. The decision might be right, might be wrong. With say greater probability, it might be right, and with lesser probability, it may be wrong. But there is a probability that the treatment might go wrong. While a teacher is explaining a concept, for example, you take a class we are doing here, when I'm trying to ask whether this is understandable or not, I get sometimes some responses, sometimes I do not get responses, but from that I need to uh, uh, predict whether the student has understood the concepts or not. So again, there is an uncertainty, right? I can observe certain variable, right? In the physical class, maybe I observe certain facial features of the student. Maybe that student is trying to say something like that. But there are certain cues which I am taking into account to decide whether the student has got whether the student has understood or not. So that is the kind of outcome. And again, the outcome is not certain, right? Even though the teacher has assumed that the concept that teacher has illustrated is very nice and the student has understood all of it, but it might not also happen, right? And again, you talk about machines. Machines, they malfunction, right? Now, the, in many cases, you might not know what is the exact cause of this malfunction, right? You try to think about different factors that can affect the health of the machine, and out of these different factors, you try to see which factor is most probable, which factor is less probable given this particular condition, right? And based on that, you try to find out the exact cause of this malfunction. Again, you talk about the robot which is kind of detecting a bomb so that is planted somewhere. So there are multiple factors that the robot should consider to detect this. So you see, you can think about plenty of examples. That is an example of the case where the agent has to work in the domain of uncertainty, right? Now let us try to crystallize what are the kind of things that are involved when we have placed the agent in the uncertain world. So the first thing is the agent has got certain beliefs. So these particular word we should be very much conversant with or very much familiar with, because whenever we are talking about state, in the earlier case, the state was basically set of propositions. But here again, the state in the uncertain world, a state is a set of propositions. But for every proposition, I do not have the certainty that I know this proposition to be true with almost the entire certainty. So that means I cannot say that the probability of one proposition to be true is 1. I cannot always say that. I can say that the probability of a proposition to be true, say 0.5. For example, today it will be raining. The probability may be 0.5, right? So that means now your state description is a set of such probabilistic beliefs, say alpha 1, alpha 2, and something like that. And these are kind of belief that the agent has got on particular propositions, right? And that is because we can observe the world partially, not entirely, right? Now, in the face of this, we have to reason with uncertain knowledge or belief. So earlier we had something like, say, we have P implies Q. We know that P to be true. With certainty, I know that Q is true, right? So this kind of inference is becoming invalid in this domain. We have to do something extra, something additional. And also, we know that the outcome is also uncertain and we have to live with that, right? Now we need to have a language to represent this uncertainty or represent this belief. And we know all that the way we represent uncertainty mathematically is what we call as probability, which is basically invented as the calculus of gambling, right? So we'll be dealing with all probability and other thing. Now let us try to compare between the world of certainty and uncertainty. So whenever we talk about world of certainty, we talk about CSPs. In CSPs, we have got states and variables. And what do we mean by a state? A state is basically a particular assignment of the variables that we know that that is true in CSP, right? Now, the constraints, they eliminate some of some worlds. So what we can get? So we have, say, n variables. So x1, x2 to xn, right? Now here you can assign say true. Here you can assign so all true. So let us take binary CSP as an example, right? So this is one world. The other world is you have say true here, say false here. This is another world. So these are all possible worlds. That means we have got 2 to the power n possible worlds. And out of these, the constraints, they eliminate some of the worlds. So this set of worlds, valid worlds, is a subset of these 2 to the power n all possible states. We eliminate. And whatever that is being remaining, those are our world in the CSP domain, right? Now, in the probabilistic domain, in contrary to elimination, we do not eliminate any world. We say that every world is probable. So we have a probability that x1 equal to true, x2 equal to true, and xn equal to true something. Also we have a probability x1 equal to true, x2 equal to true, and xn equals to say false, right? But what you can say that this probability is say less than this probability. Some world are more likely than other. So that you can say. So one such example we can talk about quickly is that let's say we have got two variables. One is temperature, other is weather. So this particular example we will be using to illustrate the ideas going forward. So the temperature, the domain of temperature is hot and cold, and the domain of weather is sun and rain, right? Now you can say that temperature, when temperature is hot and weather is sun, so that combination is true. So this is a valid word. But hot and rain, this may not be a valid word, something like that. So you're certainly saying that this combination is valid or invalid, is a valid word or invalid word. But in probabilistic sense, we can say that every word is valid, but probability of hot and sunny is more probable than probability of the word hot and rain, which is 0.1. So that is the kind of difference that we will be living with. So, as you understand that this particular domain of uncertainty will be captured using the language of probability. So we'll be having a very basic review of the probability rules. I think you are all aware of these kind of rules. So I'll be going through very quickly on this particular part, but again, I'll be spending on some of the probability concepts which will be kind of bread and butter for this particular module. So I don't think we have that much of time today. So at this point, let me stop here. So if you have any questions or doubts at anything what we have discussed till now, I'll be happy to answer. Okay, so if there is none, we'll meet in the second half to have a demonstration of the one of the SAT tools. There are many, but we will be discussing the GSAF tool. Okay, thank you. We are done for today.
Excuse me, sir.
Yeah, sure.
Sir, can you upload the CSP slides from previously? Didn't find it in the course website. And
Oh, didn't I do that? Didn't I do that?
I guess no, sir.
Okay, I'll do that. I'll do that. Sorry about that. I'll do that. Anything else? Okay, thank you.